Hello, my name is Angelica Vidas, and I will be doing some examples on partial fraction decomposition. So first, we are going to do some examples that involve setting up. So sometimes the setup portion is really confuses us at times. Um, so let me start. Okay, example one. So integral of x squared plus x minus 1 over x squared plus 4 squared. Okay, so this is our question. Um, if you notice right here, our denominator has a higher exponent value than our numerator because there's a squared out here. So 2 times 2 is 4, making the highest exponent value of the denominator being x to the fourth, meaning we don't have to do long division. Okay, now, how do we break this up? So it's very important to know. So here's our first. So you first got to take basically the basic form of this because the whole point is we're breaking this down in order to be able to solve it. Um, so in our case, we're going to take the inner x squared plus 4 as our denominator. Okay. Um, wait, let's change this real quick. So x squared. All right, so let's make this x cubed, x squared plus 3. Okay, sorry. So our new prompt is x squared plus x minus 1 over x squared plus 3 all squared. As I was saying, first we're going to do x squared plus 3. And why x squared plus 3? Because we can't simplify it anymore. And so this is one of the most simplest forms that we have. So we're gonna write this first, right? And the numerator, that's going to be ax plus b, because according to our rules, this is an equation. It's x squared plus 3. Now, would we do this if our denominator was just x squared? No, we would not. So if our denominator was just x squared, so if we had just x squared, and we write it right here in the corner, um, it would just, for example, it would just be a. It would just be a over x squared. Why? Well, because it's just x squared. It's not a whole equation. Okay. Same idea we're going to hold up. Now that we took the basic form, now we're going to include the whole thing right here. X squared plus 3 squared because we're taking into account this whole, like the squared portion. We can't just have just another x squared plus 3. You can't have the same denominator. So we're just going to square. We're just going to involve right this format. X squared plus 3 all squared. And this is going to be cx plus d. Okay? So this was just setup only. So this is basically how the setup looks like. Now, um, you might get questions where you get ax plus b first. Usually, sometimes we would get a over some value plus b over some value. But in our example right here, we start off with an ax plus b and we have plus cx plus d. Okay, now our second example, the same thing. It's just setting up. Um, a little different. So our second example is going to be integral x with x to the fourth plus x cubed plus x squared plus 5 all over x to the fifth x fourth plus x cubed. All right. So if you've noticed, we have x to the fifth in the numerator and x to the fifth in the denominator. Meaning, we can't set it up yet. We actually had to do long division at this point. So when we do long division, it's very important to remember that the okay, okay, so the top is gonna go inside x fifth, x fourth, x cubed plus x squared plus 5. And then the bottom is gonna go outside x fifth plus 4 plus x cubed. Um, how would we remember this? Okay. So sometimes, personally, sometimes one can get confused. I would like to treat this as if, let's say we have 10 over 5, right? And 10 over 5 is equal to 2 because we divide it. That's how it looks like. The 5 on the outside and the 10 on the inside. So the 2's out here, right? But if we were to write 5 over 10, that would not equal 2 because we wouldn't, if we were to simplify it, it would become 1/2 because we are saying 10 is out the outside and 5 is the inside. Okay, so these two are vastly different um answers, 2 and 1/2. So I would kind of think of this as this idea. Sometimes it's kind of easier to imagine in normal numbers. Okay, so with that in mind, let's erase this real quick because we still need the space. Okay. All right. So what are we going to multiply in? If x to the fifth plus x to the fourth plus 3x plus x cubed, going to multiply 1. Why? Well, because they're all um 1x to the fifth, 1x fourth. So we just only got to multiply 1 in. And now, important to remember, we are subtracting all the way. So you might be wondering, but they're even. Okay. So this is what we're going to do then. And we write this here. So remember parentheses, we're subtracting. You're subtracting, like how we, like in the example that I showed, with the 5, 5 by 10, we put the 2, it's 2 times 5, right? Times 5 is 10, and we're subtracting it, it's 0, and we got 0. The whole point is we're trying to see, will we get a remainder, or will we not get a remainder, right? So right here, um, x to the fifth crosses out because what's x to the fifth minus x to the fifth? 0. X to the fourth minus x to the fourth? 0. X cubed minus x cubed? 0. So then we bring down our remainders that we have left, which is x squared plus 5. Now, can we go any further? No, because the smallest exponent I had right here is x cubed, so we stop it to here. This is our remainder. What do we do with the remainder now? Okay, so remember the form qx plus rx over, okay, so this portion right here in the denominator is going to vary from question to question. In our case, our denominator is going to be x to the fifth plus x to the fourth plus x cubed. Okay, so with plugging in the values that we already have, um, our QX is our quotient. It's this, right? So it's gonna be 1 plus, right? Meaning our RX is our remainder, which ended up being x squared plus 5 over x to the fifth plus x to the fourth plus x cubed. Okay. With that in mind, um, now we're gonna separate onto the a and b, right? So this is step one, and this is step two, and now we're in step three. All right. Is our true, actually, our true step one is here, but I'll explain why. One plus x squared plus 5 over. Okay, so you have 5, 4, 3. So the max we could take out of x's is x cubed. Meaning you have x squared plus x plus 1. Okay. Now, as I've mentioned before, how are we going to separate this? First, I would involve, remember, gotta involve the quotient. So when you actually, if you actually, and solving a question like this, remember when you take the integral, the 1 is going to be involved because it's still part of this answer. We're just saying, okay, so this remainder right here, it's the rest of what we found here in part 1, but the 1 is the quotient, right? So they're both kind of like a package deal. So you can't separate one from the other. So you're gonna 1 plus, right? Um, this is gonna x cubed is gonna be x. A. Why is that? Well, because imagine um x cubed but like this, right? Remember the simplest form and then the whole thing. Okay? Plus b over, now we're involving the x cubed. X cubed plus our denominator is going to be x squared plus x plus 1. But like the other one, this is going to be cx plus d. And this is the setup for this one. So we can see right here, this was the setup for this one. The last one was setup. Okay. So to reiterate from example 1, um, we take the inside, which is simplest form, and it became ax, the denominator for ax plus d plus b. And then we took the rest of it, and it became the denominator cx plus d. So we kind of like split them, so it could be the more simplified version. Okay? And that one like took a lot less work. Now this one. First thing should be noted, look at the exponents, because technically I made mention of this right here. Looking at the exponents, we want the denominator, the highest exponent in the denominator, to be the highest value. Since we have right here a 2 and another 2. 2 plus 2 plus 2, 2 times 2 is 4. So it would be x to the fourth, the highest denominator exponent value. And now right here in the numerator, it's just x squared. So we could just keep going. We could um, do the partial fraction. Now here, you have x to the fifth in the numerator, x to the fifth in the denominator. They're the same. We don't want them to be the same, and we don't want the numerator to have a higher exponent value than the denominator. So then what do? We do long division, as shown here. Our 1 is our quotient, and our x squared plus fifth was what was left over. Okay? And then from here on, we decide to break it up, right? Because if I was multiplying the x cubed into this equation, x squared plus x plus 1, I'm going to go back and get x to the fifth plus x fourth plus x cubed. Now, here, I included my 1 because it is still part of this. It's the whole thing. We're solving this whole section. Unlike here, where it's just this one fraction. No, um our decomposition is going to involve this whole thing, including the 1. Okay. So then I remember I made mention that imagine x cubed as x parentheses cubed, right? So the inside, which is the simplest form, which is x, a over x, plus bx cubed, right? Which is the whole thing. And now the cx plus d is x squared plus x plus 1 because this is how, can't really simplify it any more than this. Can we actually? No, we can't. The reason being is because right here, to be able to simplify it, if this was a 2x, then I would be like, okay, we can split this apart. But since this is x, we can't. Um, rule of advice. So if we were to assume this is x plus 1, x plus 1. Um, Very important to note, right here, these end values, these ones, when multiplied, they should equal to 1. Okay, got that down right here, 1. But when we add them, it should equal 2. But we have 1 here, right? And we can't say, oh, maybe it's subtracting, or maybe one of this is 2. But remember, multiplication, this end would have had to be 2. So very important to note to take into account. All right. Now, an example that doesn't just involve setting up. The integral of example 3, 2x squared plus x over, let's say we're already given this, x times x plus 1 times x plus 2. Okay. What's our a going to be? It's going to be a over x, right? Oh, wait, very quickly before I continue. Look at our exponent values. X squared, right? You'd be thinking, can't this be the highest value? No, because right here you have x, x, x. 3x's, meaning x cubed in the denominator. So our denominator is still has the highest exponent value. So you can continue. say a over x plus, this is going to be b, x plus 1 plus, it's going to be c over x plus 2. Pretty straightforward, right? Okay. X plus 1 can't take simplest form of that. I mean, it is already in its simplest form. X plus 2, same thing. X, yeah, can't really simplify that anymore. So, now we're going to actually look for A, B's, and C's. So we're not setting up anymore at this moment. We're not just setting up, I'm sorry. All right. So usually how I like to write it is basically one way you can imagine it is we want to get everything on the same, above the same, over the same denominator, right? So one way you can kind of think of it is we have A, right? Over X, and then B and C have X plus 1, X plus 2. So X plus 1, right? Then multiply the top and bottom, right? Plus, same thing here, except this is going to be for B, it's going to be X and X plus 2. Going to be over X plus 1 times X plus 2 plus, ooh, all right, C over C times X, and C times X plus 1 because we don't have X or X plus 1 on C. We just have, it's just over X plus 2 plus 2 X X plus 1. Oof. All right. Rewriting that took a while. So now we see they're all in the same denominator, although kind of different orders, but it is, they both have, all three of them have X. All three of them have X plus 1 and X plus 2. So now we have them all in the same denominator. So this is actually what's going on. Um, when we do this, do you have to do this for every single problem? I would say it depends. You might have some cases where you only need to multiply one of these values, right, to match the exponent, right? I Word of advice, I would pay attention to the denominators. If it looks like this, um, multiply them all into it. If it looks like, oh, this is like a simplified version of like B or something, like our last question that we had here, right? In this case, we would just have to multiply A by A squared because it's just and X squared plus X plus 1, right? Because we only need X squared to make this make we only need X squared to turn our X into X cubed to match B. For B, we would just only multiply it by X squared plus X plus 1. Why? Well, because it has an X cubed, there's no reason to multiply an X if we're going to turn both A and CX plus D their denominators to include x cubed, right? So it's kind of redundant to multiply x to the denominator b and x cubed to a if we can just turn the x into x cubed. Okay? Really quick note, but important. Just check your denominators. Okay. So 2x squared plus x equals. So quick note, I would expand these two. So I would write it like this real quick. So this is going to become x times x is x squared, right? X times 2 is 2x. 1 times x is x, and 1 times 2 is 2. Okay, quick note. This in turn becomes ax squared plus, we add 2x plus 3 and plus x becomes 3x plus 2. Would you, if you feel comfortable doing, I would feel comfortable doing this for these types of equations now. If you feel comfortable doing it for these two, it's fine as well. As long as it helps you remember what this ends up. For example, if we multiply x into x plus 2, it'll become x squared plus 2x. Similar idea right here. X squared plus x. All right, so we're going to match up the like terms. We have ax squared plus 3x. We're going to multiply an a. Sorry. 3ax plus 2a plus bx squared plus 2bx plus bx squared plus bx. First glance, this does look kind of long, right? But remember, we're going to combine, we're going to make set equal to like terms, right? So I guess let's do some color coding, just a little bit. So let's start with the x squared. So we're involving the 2x squared, ax squared, bx squared, the cx squared. How are we going to write this? Just like so. 2 equals a plus b plus c. Okay? Now the x. X is going to involve 3ax, 2bx, and cx. So x is, the constant in front of it is going to be 1. So what we're taking into account is we're just factoring out the x squared on this whole equation, right? So we're just left with our constants. Same idea with this x as well. Constant is 1, and the other constant value you're going to pay attention to is 3a plus 2b plus c, right? Now, you might be thinking, okay, we're done. We're actually missing 2a, but there's no constant value at the end. There's like no plus 1, plus 10. No. Meaning, imagine there's a imaginary plus 0 at the end. So, 2, we're going to make 0 equal to 2a. All right. Whew. So, first thing I would look for is a, because it looks like the easiest we could do quickly. So, if we divide both sides by 2, we are going to just be left with 0 equals a. Why is that? Well, because 0 over any number is equal to 0. Now, if we had the denominator be 0, that's undefined. So, luckily, we don't have that situation. Now, wherever we see a, we're going to plug in 0. So, for our green, if I were to plug in 0 for a, I'm going to be left with b plus c. For this a, 1 equals 3a plus 2b plus c. If I were to plug in a, if I would plug in 0 for a, we would be left with 3 times 0. So 3, 0, right, plus 2b plus c, right? 3 times 0 is 0. I'm just left with 2b plus c. What do we do in respect to this? So let's isolate the c, right? Let's find c. 1 minus 2b equals c. Let's try to find c first. Let's try to find c. Let's make this equation. Okay, so with this in mind, where we see our c right here, we are going to replace the c to be 1 minus 2b. Plus 2 equals b plus 1 minus 2b. So what's b minus 2b? Well, it's going to be negative b, actually. 2 equals negative b plus 1. Add 1 to here. I'm going to have 3. Actually, wait. I'm sorry. If I were to subtract 1, um, then I would have 1 equals negative b, which would in turn become negative 1 equals b. So let's rewrite this one so I can see it better. So 1 minus b. That's essentially what's going on. Okay, so we found our B, our A. I need our C. But luckily for us, we can now plug in for B. So we got 1 minus 2, negative 1 equals C, right? 2 times negative 1 is equal to 2. 1 plus 3 equal, see, I'm sorry, not 3. 1 plus 2, which in turn becomes 3 equals C. All right, so we got our C, A, and B. All right, now we're ready to plug in these values to our A, B, and C. So we got integral 0 over x plus negative 1 over x plus 1 plus 3 over x plus 2. Okay. Are there bounds? No, there's no bounds. So we're good on that. dx. Wow. So 0x, what did that become? Well, 0. 0 over any number is 0. So we're just left with negative 1 over x plus 1 plus 3 over x plus 2 dx. Okay. So taking the integral, we can take this integral by separately. So we can color code it real quick. So first, let's do the integral of negative 1 over x plus 1 dx. So let's take out the negative, and then we're going to take the integral of 1 over x plus 1 dx. Okay. And a lot of people can assume from this point on, okay, the answer is going to be ln x plus 1. Yes, that is true. But technically, we had to do use of for the x plus 1 because you can't just technically straight assume that's going to be this because the rule is for 1 over x, the derivative, the integral of 1 over x is equal to ln x. So we kind of had to get it into a similar format. And luckily for us, our x plus 1, the derivative of that is going to be dx, just 1. So 1 over u, right? That means we don't have to plug in any other value right here at the bottom or at the top. And we are given the negative of ln u. I didn't mean that. Sorry, du. Um, equals negative. Now we gotta plug back in for you. ln x plus 1. All right, that's for the first part. Now, what about the second part? The integral of 3 over x plus 2 dx. Right, so like I said, take out the constant, 3, and outside 1 over x 2 x. Okay, same idea. Technically take the derivative. So since we're doing two u subs, do not confuse, I'm going to change u to be w x plus 2 dw is equal to dx. And this is equal to, if you were to rewrite it, 1 over w dw. So this is 3 ln w 3 ln x plus 2. And so when we combine both, we have negative ln x plus 1 plus 3 ln x plus 2 plus c. This is our final answer. Negative ln x plus 1 plus 3 ln x plus 2 plus c. To reiterate real quick, essentially, what we're doing here is we split it up. Then we decide to multiply in the a's and the b's, um, as shown right here. And then we decided to put together like terms, right? And just imagine we factored out either the x squared or the x, right? Then we try to calculate and try to find for a, b, and c. A was easy, or it's basically divided 2 to 0, and it was just 0 equals a. And then we had to work a little bit more to find b and c. So right here I isolated c, right? Because there's no value. You can have a 3 or a 5, right? And so then I just wrote it as 1 minus 2b. Okay, so c is equal to 1 minus 2b. Then I jumped over here, right? So where I saw the c right here, I replaced it with 1 minus 2b, so we can at least find b. Okay, and then I subtracted the two b's, which left me with a negative b. I subtracted a 1 to the 2 because it's a positive 1, and then I was left with a 1. And we had 1 equals negative b, but we want b. So then I pass over the negative, and b became negative 1. This in mind, for right here, we jump back to here. I plugged in negative 1 to where b was. So we had negative 1 times 2. Negative 1 times 2 is going to be negative 2, but we changed it into a positive because we have a subtraction here. So we had 1 plus 2, which became 3 for C. With this all in mind, wherever we saw A, B, and C, we decided to replace them with the respective values that we calculated. Since 0 over x is equal to 0, we decided to cross it out. And we were just left with -1 over x plus 1 plus 3 over x plus 2. We took the integrals of both. I made a mention that technically for x plus 1, x plus 2, those values, you have to do u sub technically, because the rule is for 1 over x is equal to ln x, right? So we had to technically change it into a form that looks like that. Um, is it okay to assume at times? But let's say we have 2x plus 1. You can't really assume that because you're gonna have a leftover 2. So yeah. And just remember and be very careful. And then I took the integrals separately for both, and then I combined them at the end. Since we had no bounds, we just had a plus c. All right. Um, Next video, we'll talk about another one of these examples, except it's not setting up, we're actually working. This is it for this video. Um, and I hope this was helpful to all of you, Thank you.